Okay, in this video we'll be looking at some review questions for the topics of exponential equations, arithmetic series, and geometric series, which are of course just sums of all of the terms in an arithmetic sequence or a geometric sequence. So in our first problem, researchers have found that a specific culture of bacteria increases according to this formula, and it tells us then that n is the number of bacteria that we have and t is the number of hours. Alright, part A, the number of bacteria present at the start of the experiment, that means that no time has passed. So because t is equal to 0, we can substitute into the formula that n is equal to 150 times 2 to the power of 0. Now 2 to the power of 0 equals 1. So now we've got 150 times 1. Remember, any number to the power of 0 is 1. And so we've got then 150 at the start of the experiment. Another way that you can see the number that is the initial value would be that when you're looking at any kind of function, k times an exponential function, we know that that value of k, the coefficient in front of, but not including the power, only the coefficient in front represents the initial value. So if you ever had something that looked like this, don't get fooled. This does not mean that the initial value is 2, that there is a hidden coefficient of 1. The 2 to the x is the power and is not included. It is the number in front that represents the initial. And if that confuses you a little bit, just remember that at the start, or the initial time, that means that t is equal to 0 and you can substitute it in. Anything to the power of 0 is 1. Alright, so that's the answer to part A, 150. Part B, the number of bacteria present after 3 hours, and so n is now going to equal 150 times 2 to the power of 3. Let's do this on the calculator. So 150 times 2 to the power of 3 gives us 1,200 bacteria after 3 hours. And part C, the number of hours it would take for the number of bacteria to reach 19,200. So now they've given us the number of bacteria. So let's substitute 19,200 in for n. And we're trying to figure out what t is, the number of hours, so we have to leave t as the variable. Now a good way to solve this, let's just think about what would be the right calculator method. Is it possible to have a fractional or decimal number of hours? Sure, it's possible it would take 5½ hours, and so a table is not the best approach here. Let's instead use a graph. So in y equals, my left-hand side is 19,200, and my right-hand side is 150 times 2 to the power of x. Now before I graph this, I think that looks right. Before I graph this, I should go into the window and set my window up. I've got a constant function of 19,200. So I have to make sure that my y values go at least past 19,200. So I'm first going to adjust my y max to something bigger. Let's say maybe 19,500. 19,500. Safely above. And let's just think about the x min. If my bacteria is starting out at 150 and they're growing to 19,200, that's well off in the future. So I don't need to be looking at any negative values. Let's just start from, I like to start from -1 just so I can clearly see the y-axis. And how many hours might this take? Well, I really don't know. Let's leave it at 10 and just see whether we can see the intersection. There's the 19,200 constant. Here comes the growing bacteria function, and there we can see the point of intersection. Now, if I'm going to show all of my work and I want to demonstrate that I've solved this with a graph, then I should just quickly draw a sketch of what I see. And so I've got my constant function here. That was my y1 equaled 19,200. And then I've got my growth function starting very low and coming up like that, and that is my function of y2 equals 150 times 2 to the x. And the point of intersection right there has got coordinates. Let's find them out. Second trace 5 to go into the calculate menu and the option intersect. First curve, yes, is y1 equals 19,200. Second curve, yes, is the right-hand side of the equation. And we need to guess. So I'm going to move the cursor fairly close to that intersection point. It's not very close, but it's going to be close enough because it's, oh, well, yeah, there, that's very close. And I see that they intersect when x is equal to, wow, exactly 7. I'm quite astonished that this ended up being an integer. I guess then it turns out you could have done this with a table, because you would have ended up seeing 19,200 on your table. But I think with most questions like this, where you could have a decimal number of hours, that would be a bit of a risky proposition. I think you're better off using a graphical method, just in case the given number doesn't appear on the table. And we ended up then with an intersection of 7, 19,200. So that's how you show your work for the graph to justify why the number of hours is 7. Let's move on to number 2. Here we've been given a sequence of numbers. I need to show that the sequence is arithmetic. To show that something is arithmetic or geometric, I must take pairs of numbers and write them in reverse order. So I'll take the second one minus the first one. I'll take the third one minus the second one. I'll take the fourth one minus the third one. And in each case I'm going to calculate the difference. 23 minus 28 equals negative 5. 18 minus 23 is negative 5. 13 minus 18 is negative 5. I can see that I have a common difference. And because I have a common difference, that is what makes it an arithmetic sequence. And you might notice that this difference that we get of negative 5 can be seen. What did I do to go from 28 to 23? I added negative 5. From 23 to 18, again, 18 to 13, I added negative 5. I know you might think of it as simply subtracting 5, but, well, anyway, I think it's easier to think of as plus the negative value. It's a negative difference that we're adding. Anyway, part B, an expression for un, the general term of the sequence. And so, let's see, we know that in general, by looking in the formula booklet, that un is equal to the first value plus n minus 1 of the common differences. So let's substitute into that. That means that un is going to be equal to, actually I'm going to write it a little bit differently up here. So that means that my un is equal to my first term, which is 28, plus n minus 1 times our common difference of negative 5. Excuse me. And the sum of the first 25 terms of the sequence, there we go, S25 now, and this time we'll use the arithmetic sum formula, which would be, maybe I should remind you what the formula is in case you don't have it handy. So the sum of the first n terms is going to be n over 2 times, now I've actually got a choice of two formulas in the formula booklet. One of the formulas is helpful if I already know my value of d, and the other formula is helpful if you already know your last term in the sequence. Here I don't know what my last term is because I haven't calculated u25, the 25th term. So because I don't yet know what my last term of the sequence is, I'm better off using the formula that involves the d value. And that's going to be 2u1 plus n minus 1d. So in our case then, we've got 25 over 2. And then our u1 was 28. In this case, remember that n is 25. So our n minus 1 becomes 25 minus 1. That is to say that we're adding only 24 of the d's, which are negative 5. I'm going to put all of this into the calculator now. 25 divided by 2 times, and yeah, I can understand that you might feel it's important to put the 25 over 2 into parentheses to ensure it's treated as a single number. Alright, we're multiplying by this bracketed expression of 2 times 28 plus 25 minus 1. I have to put this one into brackets because subtraction and addition are the things that are done last in order of operations. So we need to tell our calculator, no, you got to do it first. And this is multiplying negative 5. And so, because the multiplications will happen first, these two will be multiplied and then added to the product of 2 and u1. Let's close the parentheses and calculate, and we get an answer of negative 800. Let's move on to number 3. A geometric sequence has got u6 is 24 and u11 equals 768. Alright, you should remember how to do these kinds of questions. They've given us two advanced terms in the sequence, so we have to build a system of two equations with that given information. In a geometric sequence, it's very important that I would actually even circle the word arithmetic or geometric to remind yourself through the question to use the correct set of formulas. So u6, another way of writing u6 is u1 r to the power of 5. And so that equals 24. And in the second equation, u1 r to the power of 10 is equal to 768. So what am I going to do with these two equations? If this was an arithmetic case, then I could probably use polysimilt. However, this is a geometric case, and so my technique is to take my bigger power of r, remember that equation? And I'm going to divide that equation by the equation that involves the smaller power of r, and r to the 5. The nice thing about this technique of dividing one equation by the other equation is that the u1s will cancel. And now then, if I have 10 r's on the top and 5 r's on the bottom, 5 of them are going to cancel on the top and the bottom, leaving me with only r5 on the top. 768 divided by 24 gives me 32. And so r is going to equal then the fifth root of 32. As I bring that fifth power across, it becomes a fifth root. And I'll find the fifth root button by pressing math. First I have to tell the calculator that I'm going to be taking a fifth root. So I type in the 5, and now I press math and go down to option 5, which says any kind of root. So in this case the xth root. I've already typed in my value of x, a fifth root. And so it's going to be now the notation has changed, the fifth root of 32. And we get an answer of 2. Now, the question is asking us, by the way, to find an expression for un, and we know that in general un is equal to r to the n minus 1. So, that's not right, sorry, it's equal to u1 times r to the n minus 1. So we have to find not only the r value, but we also have to find the u1 value. I don't need to find the value of n because I'm supposed to leave it in terms of n, the general term. Alright, so now I've got my r equals 2. How do I find my u1? Why don't I substitute back into the simpler of the two equations? So I have u1 times 2 to the power of 5 is equal to 24. According to order of operations, I must do the exponent first. And so u1 is 24 over 32, which simplifies to 3 over 4. And so then our general term will be un is equal to u1, which is 3 over 4, times r equals 2 to the power of n minus 1. And there's your answer to part A. Part B asks us to find u17. So of course we just have to substitute the 17 in for n now. So u17 equals 3/4 times 2. Yes, that's right, to the power of 17 minus 1, or to the power of 16 if you like. And on the calculator, let's see, 3/4 times 2 raised to the power of 16. And it gives us 49,152. And part C asks us to find the sum of the first 15 terms. So just to remind you again that in a geometric sequence, you can see this in the formula package, we'll have two renditions of this formula. I prefer this one, which is the second one given, but honestly you can use either, it won't make a difference. There's no advantage to using one over the other, like there is in an arithmetic series. So let's substitute what we know. u1 is equal to, we solved it to be 3/4. 1 minus r to the power of n, which in this case we're looking at sum of the first 15 terms, over 1 minus r. Alright, so I've got, I'm going to be a little bit more careful now about using parentheses, because this is a much more complicated expression. So I've got 3/4, which is multiplying 1 minus 2 to the power of 15 I'll take that result and I'll divide it by, let's be careful now about parentheses, 1 minus 2, so that I'm dividing by that entire denominator. And I get 24,575.25. And I think that you would have the option of rounding to 24,600, which is 3 significant figures. But the question doesn't require it, and that's just wasting time. If you've already got a nice exact value, why continue? Okay? Alright, number 4. Here is an exponential. We can see that this is a decay function because we're decaying. Now let me just remind you about the theory of exponential growth and decay. A growth curve will look like that, while a decay curve will look like this. In both cases, I'm talking about a rather simple function of y equals a to the power of x. It's an exponential growth or decay function because the x is up in the exponent. The base of a tells us whether it's going to be an exponential growth if a is bigger than 1, or if it's going to be an exponential decay when a is in between 0 and 1. Okay? Now there's a couple of characteristics of each of these graphs. Both of them will intersect the y-axis at 1. Now if we change the function slightly so it became k times a to the x, well then our initial value is no longer 1, our initial value is now k, and so instead the intercept would become k. In this particular function, I don't have a coefficient in front of my power. I've got simply a power. I'm going to talk about this part later. And so this is effectively saying a 1 times the power of 3 to the, and the x is up in the variable, implying an exponential equation. And so our initial value in this particular situation should be 1. Now let's talk about this plus 2. This is a transformation that slides your graph up by 2 units. And so 1, if we add 2 to it, we're now dealing with a new y-intercept located at 0, 3. In fact, this shift upwards by 2 units also explains why in a regular exponential growth or decay function, we have what's called a horizontal, because it's flat along the x-axis, asymptote. Because it's along the x-axis, its y value, although the x value is changing, the y value is fixed at 0. And so we talk about this relationship of points as y is 0. That's the rule that ties them all together. And we can see that the exponential decay or growth function is getting closer and closer and closer to that horizontal line whose equation is y equals 0, but never touches it. That's what's called an asymptote. This is a horizontal asymptote. But if we slid our graph upwards by 2 because of this translation, that must mean that the horizontal asymptote, the value that this graph is approaching, has also shifted upwards by 2 units. And so instead of it having an equation of y equals 0, it will have an equation of y equals 2. So I've jumped ahead a little bit and solved part B, write down the equation of the asymptote. This equation shifted upwards by 2 units from what was regularly a what was regularly an asymptote of y equals 0 has now become, of course, y equals 2. We just need to find the values of a and b. You might not have seen how the y-intercept was 1 and then shifted upwards by 2 to come to 3. So another way you could do it is substituting in 0, comma a into your function. And so 0 is the x value, and a is the y value. And we can see that a equals 3 to the power of negative 0. Well, 3 to the power of 0 is 1. And so a equals 3. And we can do a similar process. Let's substitute in 1 and b for the x and the y again. 3 to the power of negative 1 means 1 over 3 to the power of positive 1. And 1/3 plus 2 is 2 and 1/3. If you did this on the calculator, though, they would give you an answer of 2.33 if you rounded to 3 significant figures, and either would be acceptable.